In Chapter 4.2, we're going to be non-dimensionalizing the heat equation and the boundary conditions as well. So first off, why do we bother non-dimensionalizing the heat equation? Because it does take a fair amount of time. And the obvious reason is we want to remove the dimensions or the units from the problem. Well, why do we want to do that? It's basically to make the problem easier to solve. And we'll see that in some cases, non-dimensionalizing actually simplifies the equation. And in this particular case, non-dimensionalizing massively simplifies our boundary conditions. But either way, the problem becomes more tractable because of the non-dimensional form. Also, once you've non-dimensionalized the equation, the solution is a lot more general, and so you can apply it to any problem that is defined similarly. And it may sound like there's not many problems in the world that are defined similarly, but actually one solution can solve a lot of different physical phenomena. And we'll see that when we come to a mass transfer solution that is identical in form to a heat transfer solution. Finally, we want to be able to compare the relative contributions from different physical phenomena. And what I mean by that is looking at non-dimensional numbers like the Reynolds number, for example, which compares inertia to viscous forces in flow. In heat transfer problems, we'll be more interested in comparing convection to conduction, but presenting a non-dimensional form enables us to make those comparisons more easily. All right, without further ado, let's remind ourselves of the governing equation and start by defining what variables we need to transform. So there's three variables in this equation that have dimensions, t, x, and z, and we're going to need to redefine each of these in order to non-dimensionalize the equation. We'll start with t, and traditionally we use the variable theta to represent temperature. We'll choose this form where theta is defined as a delta t over a delta t. In this problem, T1 and T2 are both characteristic temperatures. And so when you have two characteristic boundary values, it's quite common to take the difference between them as the denominator in your non-dimensionalization. Why we've chosen this particular form of theta is because when temperature equals T1, theta equals 0. And then when you plug in that the temperature is T2, you get that theta equals 1. So within the boundaries of this problem, we have temperatures ranging between T1 and T2, and in the non-dimensional form, that means theta ranges between 0 and 1. And intuitively, you can pick up why that is convenient, because whatever value theta is tells you what percentage of the way it is between the two boundary temperatures. Moving on to x, we use the Greek letter xi to represent our non-dimensional x position. And here it's a lot easier to non-dimensionalize it because there's only one characteristic x length in the problem, and that's L. And so if we just divide x by L, we get our non-dimensional variable xi. And we know that's right because xi then varies between 0 and 1, as x varies between 0 and L. And it's the exact same story for our z position. We use the Greek letter zeta, and in this case, zeta is varying between 0 and 1, as z varies between 0 and L. All right, the next step here is to actually transform the coordinates of our dimensional equation into the coordinates that we have just chosen for our non-dimensional coordinates. That is, we want to transform the t, x, z's into thetas, xi's, and zetas. So to do that, we're going to use the chain rule. We'll start with the first term, which is d squared t dx squared. And you can break that into two pieces. There's the d dx and there's the dt dx. And we want to rewrite those in terms of the non-dimensional parameters. And you might want to have a look at the chain rule to remind yourself. It looks a lot like multiplication here, right? It's not exactly correct, but you'll get the right answer if you make it look right according to multiplication. So here, it looks like the ddc on the bottom denominator of the first expression cancels with the ddc on the top numerator. It's not exactly canceling, but it works. Those first two terms are equal to ddx. Likewise, we want to take the dt dx term and transform that into something that looks like d theta dx. And so to do that, you first differentiate t with respect to theta, then differentiate theta with respect to xi, and then differentiate xi with respect to x. So it looks a little bit complicated, but actually this is second nature. You've done this hundreds of times before. We'll move on to the second term in the heat equation, the d squared t dz squared term, and we'll do the exact same thing, but this time we're differentiating with respect to zeta. So basically, it is what it is. All right, so those are the two terms in our new non-dimensional equation that we're going to need. In order to calculate those values like dt d theta and dx dx, we actually need to implicitly differentiate the non-dimensional variables. And work with me. We've just got a couple more steps in this process, and then all the steps will come together to simplify our equation. So we remember that theta is defined as such, and if we implicitly differentiate that, theta is a variable and t is a variable, but t1 and t2 are both constants. So implicitly differentiating, we get a derivative t on the right-hand side and a derivative of theta on the left-hand side, and then the constant is the denominator. So we do the same for x and xi, implicitly differentiating dx equals 1 over L dx, and zeta, if we implicitly differentiate, d zeta equals 1 over L dz. So those are implicit definitions of the non-dimensional variables. I'm going to transfer them over to the next slide. They're there on the bottom of the slide. And now we'll come back to that governing equation, which we performed the coordinate transformation on. And if you put it all together into one line, it's a little bit messy looking, but break it down. This is actually quite easy. Our first substitution is going to be dx dx, and if we look down at the definition, dx dx equals 1 over L. So let's look at what this looks like. We substitute in 1 over L for dx dx. dt d theta basically has the value t2 minus t1. We don't try to substitute out the d theta dx because that's actually the derivative that we want. And we don't have an implicit relationship between those two variables that we've yet defined, right? But we do have a relationship between dx dx. We substitute that in again. Then we come over to the z term, and we substitute in d zeta dz, which is 1 over L. We substitute that in both places that appears, and our dt d theta is the same as it was for the x term. So it's a little bit of algebraic mess, but it is quite simple. Both of these terms are multiplied by t2 minus t1 over L squared. We can divide both sides by t2 minus t1 over L squared, and we get d squared theta dx squared plus d squared theta d zeta squared equals 0, which looks a whole lot like the equation that we started with, just transformed into a different coordinate system. And at this point, you're probably asking, why did we go through this onerous process? This hasn't changed the equation in any appreciable form. And you're right. it's the boundary conditions in this problem that are going to see the most effect from non-dimensionalization. So we'll go ahead and move on to the boundary conditions. So we have 4 boundary conditions, and they're written in terms of x and z and t. So we need to just substitute in from our non-dimensional definitions what those values are. So for xi, we have when x equals 0, xi equals 0, and when x equals L, xi equals 1. So that's what I'm writing in this column. And then when x equals x, well, xi is also a variable, so xi equals xi. And that's the same for the last 2 boundary conditions. All right, if we move on to the next non-dimensional parameter, zeta, when z equals z, zeta equals zeta. So that's true for the first 2 boundary conditions. And in the second 2 boundary conditions, we have one where zeta equals 0. And so in that case, z equals 0, and in that case, zeta equals 0. And when z equals L, zeta equals 1. All right, so then we do the same thing for temperature. When temperature equals T1, theta equals 0. When temperature equals T2, theta equals 1. So now that we've written out what each variable is for these boundary conditions, we can rewrite them as something that looks more like a boundary condition in the non-dimensional form. So theta of 0, zeta equals 0, and so on and so forth. And this is literally why we chose to non-dimensionalize the equation, because we've been able to write 3 boundary conditions equal to 0, and that's going to massively simplify the problem when we're solving it. We'll solve the problem, but then we need to substitute in these boundary conditions to solve for the constants of integration, and that's where those zeros are really going to help us. So, thanks for your attention, and I will see you for the solution of this problem.